Hi everyone, welcome to Team 11's Interim Report. Our project focuses on optimizing a trip to Mars. A team of astronauts is ready to go to Mars, however, issues with the weight of the rocket have delayed their launch date. Our team has been tasked with minimizing the mass of 3 systems that will be on board this first trip to Mars. The trip will include 4 astronauts and will last 180 days.
The system flow diagram shows how the system takes in 2 input variables and certain parameters and return an optimized output. It also shows the coupling between the subsystems, as one subsystem will require the output of other subsystems as inputs to complete the optimization. Overall, all 3 subsystems share a similar objective. Our first subsystem is habitat structure. The design problem is to minimize the total weight of the habitat structure while satisfying thermal, structural, and dimensional constraints. The subsystem's design parameters include Mars' atmosphere temperature and pressure, and the properties of the structure's material. 6 design variables are considered in the model, including variables that define the size and geometry of the habitat structure. More than 20 intermediate variables connect the design variables to the thermal, structural, and dimensional constraints.
Design constraints for this project included a minimum storage for food in terms of volume, as well as a minimum space that the astronauts would be able to live in. We specified maximum von Mises stress that the wall material would experience, as well as a minimum heat loss rate, a specification to ensure that our habitat would be 3D printable, and then 2 constraints to ensure that our cylinder, which we assumed would be the living space, would be enclosed within our habitat dome. Our objective function is shown below. Computational modeling was used for this habitat. The assumptions that we made included that the insulation didn't have any structural strength, that no heat loss was through the ground, and that all the materials except for the cement for the concrete would be sourced on Mars. The geometry also would be 3D printable if we only used the top half of a capped sphere. We solved this with MATLAB's fmincon function. Here you can see how our model is stable across several different starting points, all converging to the same F star. The results for the optimized design variable values are shown here, as well as the geometry of the structure that we were creating, which is a cylinder within a capped sphere. Also shown are the total mass values that would have to be carried onto a spaceship to create this habitat.
The next subsystem is energy. In this system, we solve the problem of optimizing energy production between energy sources to minimize payload mass. Our parameters cover power requirements, efficiencies of sources, and power-to-mass ratios, all of which allow us to compare energy generation on a per-mass basis. We considered solar, chemical, hydrogen, and nuclear energy sources as our design variables. Then, we defined additional intermediate variables to calculate individual and cumulative contributions from the sources, as well as the power storage and demands during the day or night. For our constraints, we specified that the cumulative power generated be greater than or equal to demand across day and night, that our storage be less than or equal to the excess, and as well as some other additional constraints for limiting source masses and contributions. And this left us with the objective function of minimizing total mass of the sources.
Our modeling approach is analytical, consisting of formulas that approximate physical phenomena. Some assumptions we had to make include approximating time-varying parameters as averages. These include solar flux, hourly power requirement, solar panel efficiency, etc. Another assumption we made was that nuclear system weight scales linearly with power output. This simplification neglects the reality that nuclear systems require a minimum mass of equipment to produce any power. Finally, we also neglected the mass of hydrogen storage equipment, assuming that a Mars colony would already have hydrogen storage for mission-critical resource production, such as fuel and fertilizer. Thus, our hydrogen energy storage mass only includes the weight of the hydrogen itself. For our optimization method, we used the gradient descent algorithm fmincon. Though a linear programming algorithm would have been better for this application, we plan on adding nonlinearities in future iterations. Here are the results from 5 separate runs with varying design parameters, including specifying minimum power contributions and varying solar flux values. To summarize these results, solar energy generation is the most efficient power generation method given a certain minimum solar flux, which depends on latitude. Beyond a threshold latitude, nuclear will outperform solar. As far as energy storage, hydrogen is a more mass-efficient energy storage solution because of its high power density when compared to chemical batteries. In future iterations, we hope to increase the complexity of our model by improving our assumptions with more accurate data and time dependency, as well as including more parameters such as temperature effects, replacement mass, etc.
Moving on to the food supply subsystem. Given the uncertainty of growing food on site, it's crucial to bring enough food while minimizing total mass and adhering to nutritional needs. From the ISS database, we identified 176 space food options detailing their mass, calories, and nutrients. We removed beverages to focus on complete meals. This is a brief look at our food database. Our design variable is a vector indicating servings of each food on board. Intermediate variables link scalar constraints with total servings, calculating overall calories through dot products. Macronutrient calories are calculated by converting from macronutrient to gram ratios, aligning with required nutritional calorie percentages based on astronaut health studies. We designed constraints to maintain astronaut health, a caloric range of 2,700 to 3,700 per day with specific macronutrient percentages. Meal distributions ensure 30% of calories are from entrees and 20% from breakfast, with varied meals every other day. Integers represent servings due to individual packaging. Choosing lightweight food could mean compromising nutrition and variety, impacting astronaut morale. Balancing mass, nutrition, and diversity is crucial for both physical and mental well-being on the mission.
For the food system, we chose to use an analytical modeling approach where we attempt to solve a system of linear inequalities. For this, some key assumptions were only solving for food consumed while actively on Mars and only using foods from the ISS database. The optimization method we used was constrained integer linear programming via MATLAB with intlin-prog due to the discrete nature of eating integer numbers of meals. Here you can see a summary of optimization results for 6 runs, the first 5 of which did converge to a final answer. And then here you can see a summary of results for the optimization variable itself, a number of items of each food type. And then some key insights are that foods that are repeatedly chosen, especially in high number, represent high value or high nutritional or caloric density foods. Also that certain constraints tend to impact the total mass much more than others. For example, variety impacted the total mass much more than entrees or quadruplet constraints. And then some practical considerations as limitations of this analysis include this neglects the volume of any packaging, so boxes, bags, pouches, etc., and that certain foods might be high in nutritional density but low in packing density, for example, peanuts versus rice. So these are 2 potential limitations of this analysis that might affect real-life results.